Alright, that's our cue to get started. So, any questions on anything from last time? Any homework questions you'd like to talk about? Alright. Okay, so just like a few announcements. So as I've already said a few times now, Quiz 6 covers lessons 15 and 16 and opens today at 9 a.m., so in 90 minutes for the 8:30 section, and closes tomorrow at 9 a.m. And as you guys know, Exam 2 covers lessons 11 through 18, opens up this Saturday, and closes on Tuesday at 9 a.m. So because of that, not only will there be an Exam 2 review this Friday, so please come with any questions if you have any, but there will also be no class next Monday, so in compensation for the 60-hour exam. So as I stressed with Exam 1, and I'm going to stress here again, please make sure you have a place with a stable enough internet connection, because I don't want the situation where, you know, the internet craps out on you during the exam, and yeah, because that'd be bad. So, extra credit 2. You guys all got my email about that? Did anyone not get that email? Okay. So yeah, I sent out a challenge packet on Monday, so check your emails for all the rules and regulations on how to get extra credit from that challenge packet. And one thing I will mention is that the extra credit is going to be due this Saturday at 9 a.m., precisely when the Exam 2 window opens up. And I'm going to make this cutoff / deadline strict. So what that means is if I see an email from one of you guys at 9:01, I'm not counting it. So just keep that in mind. So there's that. And then office hours. So because I'm going to have office hours this Friday from 6 to 8 for any last minute questions for the exam, I'm not going to have my usual office hours tonight. So just keep that in mind. Okay. So with that out of the way, any other questions on anything you'd like to talk about? All right. Well, then let's move on to the very last lesson of Exam 2, which is increasing / decreasing functions and the first derivative test. So the premise is that basically we have to figure out, you know, intervals on which we have increasing and decreasing functions, and we have to utilize the first derivative test. Okay, so let's start off with a definition. So let f of x be continuous and differentiable on an open interval I. So if f prime of x is greater than 0 for all x in I, then f of x is increasing on I. Okay. So that's part A of the definition. For part B, as you might have guessed, well, if f prime of x is less than 0 for all x in I, then as you might have guessed, in this case, f of x would be decreasing. Decreasing on I. Okay. So to give you a visualization of what I mean by this, let's go ahead and take a look at the following. So to see what an increasing function looks like within this, based off this definition, so here's a function that, well, clearly is increasing. If x is increasing, that means y is also going up, / increasing. But to view the idea of an increasing function in light of differentiability, well, let's take a look at particular points. So let's take 4 points and look at line segments corresponding to slopes, or just corresponding to the tangent lines. So if we take some small line segments corresponding to the tangent lines at each point, then what you'll notice is that each of these slopes here are positive. So slopes of tangent lines are greater than 0 in the context of an increasing function. Okay, so in the context of a decreasing function, it's going to be similar, except here we pick 4 points. 1, 2, 3, 4. What happens here is that if we take line segments corresponding to the tangent lines, well, what happens here is that you notice that the slopes of these tangent lines are going to be negative. So slopes of tangent lines is less than 0. Okay. So definition-wise, you think, okay, well, that's fine and all, but what's the point of all this? So the point is that we can use this to figure out, we can start to figure out, where are there increasing and decreasing intervals. And we can also connect this back to something we saw last time, and in particular, how to see relative extrema from an actual expression for a function, not just its graph. So recall, if f of c is greater than or equal to f of x for all x in I, then f of c equals a relative minimum. So for all x in some open interval, okay. Oh, sorry, not relative minimum, relative maximum. Okay. So, and similarly, if f of c is less than or equal to f of x for all x in some open interval I, then f of c, that's where the relative minimum comes into play. Relative minimum. Okay. So, let's go ahead and sort of find a way to connect these two. And the way to connect these two is with what's known as the first derivative test. So the premise is that let x equals c be a critical point for, so in typing this up I had a bit of a minor typo, I didn't realize this until last night, so this should be f of x, not f prime of x, so you can just sort of put a little blobber on the prime part. So i.e., so points on domain of f of x where f prime of x equals 0 or does not exist. Okay? So the first part of this first derivative test, or first dt, as I'll abbreviate for a while, says the following. So the first part says if f prime of x goes from positive to negative at x equals c, then f of x has a relative maximum at x equals c. Okay. So part 2 says, okay, basically what happens if it's the opposite? So instead of going from positive to negative, what happens if we go from negative to positive at x equals c? Well, then f of x has a relative minimum at x equals c. Okay? And then 3 is sort of the otherwise case. So else f of x has neither a minimum nor a maximum at x equals c. Okay. So let's go ahead and give some graphs to illustrate what I mean by this. So for the first part, if we say, all right, if f prime of x goes from positive to negative, then what that says is that based off of our definition, if f prime goes from positive, so f of x is increasing, to negative, so f of x is decreasing, that says, okay, if f of x goes from increasing to decreasing, then we have a relative maximum. So it goes from increasing, then x equals c, then to decreasing. So x equals c goes here. So to give you an idea of what's happening with the first part of the first derivative test, that says, okay, so if we have, if f prime goes from positive, so the slopes are positive, to negative, where the slopes are negative, and then, for instance, we could have a horizontal tangent line where f prime is 0. That says, okay, that must mean we have a relative maximum here. Right? And then similarly, if we have we go from negative to positive, we're going to have something that looks a little bit like this. So here we have f prime goes from negative to positive at x equals c. So here we're going to have a relative minimum. Okay. But otherwise, if we go from just positive to positive or negative to negative, well, there's not really a max or a min. So graphically, that looks like the following. So it looks something like this or this. Okay. So graphically, we get something like either going from positive to positive or negative to negative. X equals c. X equals c. Okay. So we either go from positive to positive or negative to negative. And just for consistency's sake, I'll go ahead and put arrows here as well. So, okay. So that's basically the whole idea behind all that. So are there any questions on any of that? I know there's a lot of expository stuff, but just a bunch of stuff that might help you understand the concepts before we dive on into them. Or some examples. Any questions before we move on? Okay. All right. So example 1, we're asked to find the intervals on which the functions below increase/decrease and find the relative extrema if they exist. Okay. So you're given that f of x equals 4x to the 5th plus 5x to the 4th minus 40x cubed. Okay. So with a problem like this, it might help to consider the following. So with this, we say, all right, it looks like we're going to have to employ the first derivative test if we need to find the relative extrema if they exist. So based off our definition, it seems like we need to figure out what the critical points are first. So let's do that. So step 1. Find critical points. Okay? So the thing is that if we take a look at our critical points definition, that says, okay, it's a point on the domain where f prime is 0 or does not exist. So what this says is that, all right, well, in this case, we just have a nice little polynomial of degree 5. And so its derivative will also be a polynomial. So the nice thing is that both f of x and its derivative will be defined everywhere. So all we need to do here is just, first off, just find f prime of x and just see when that equals 0. So first off, what is the derivative of f of x here?
(20x to the 4th plus 20x cubed minus 120x squared).
Yep, 20x to the 4th plus 20x cubed minus 120x squared. Okay? So this all equals 0. So if we set that equal to 0, let's see what the solutions to this are. So what you'll notice is that, all right, well, this doesn't really look very pretty at first glance. So let's go ahead and sort of see what we can factor out to make this look a little bit nicer. So if we look at each term here, what does it seem like we can factor out of each term to make this look a little bit cleaner?
20x squared.
Okay, so if we factor out 20x squared, then we get, well, first term becomes x squared, second term becomes x, and then the third term will just become 6. But now you'll notice this is something that's a lot easier to work with, right? Because now we should be able to factor this quadratic. So we have 20x squared times the product of what two factors? So x and x.
Is it 3 negative 2?
Yeah, so x plus 3 and minus 2. So if we set all that equal to 0, well, that should pretty quickly tell you that the critical points here are just x equals negative 3, 0, and 2. So that's step 1. So nothing too crazy with that. So any questions on that part before we move on? Okay. So now here's where things start to get a little bit less familiar. Because step 1 was basically just a rehash of what we did yesterday. So step 2 is now we have to make a number line. A number line with the critical points, or CPs, and domain. Okay? So what do I mean by this number line? So in this case, all I have to do is say, all right, well, this number line of which I am speaking of is the following. So here's our number line, and we're going to label the number line with these 3 critical points. So we have negative 3, 0, and 2. And I'm going to put an f prime here to denote the fact that we're working with the function f prime. So what we're going to do is we're going to use this number line. So use this number line. So use this to find increasing / decreasing intervals. Okay? Alright, so here's how this is going to work. So the thing is that we already know that the only 3 points at which f prime equals 0 are negative 3, 0, and 2. So I'll label 0 here to indicate that. So what that means is that on each of the remaining 4 intervals, they either have to be all positive or they either have to be all negative. So if that's the case, if we pick a point and say negative 3, 0, if that point is positive, then that means all the points in that interval have to be positive as well. And or at the same time, if one point's negative, then they all have to be negative in this case. So if that's the case, that says, all right, we only have to pick 1 point in each of the remaining 4 intervals to get increasing or decreasing. So pick x values in each interval. Okay. So what I mean by that is that we have, all right, so our remaining intervals are, well, negative infinity to negative 3, negative 3 to 0, 0 to 2, and 2 to infinity. So we have negative 8 infinity, comma, negative 3, negative 3, comma, 0, 0, comma, 2, and 2 to infinity. Right? So if I were to pick a point and say negative infinity to negative 3, pick your favorite point in that interval.
Negative 4.
Negative 4? Okay, good. It's good thinking too, because that's exactly what I have in my notes. So there's that. All right. And then same thing with negative 3 to 0. Someone else pick your favorite number.
1.
1, good. Wait, 1?
Or, sorry, not 1, negative 1.
There we go, negative 1. But we'll go ahead and use 1 in the next interval, that way. Okay. And then for 2 to infinity, yeah, we'll pick 3. All right. So now the reason we're doing this is to say, all right, now that we have our desired x values, we were going to say plug in x values into f prime of x to see if positive or negative. So the thing is that in this case, we don't care about the actual value. We only care if we actually get a positive or negative sign out of this. So only need sign, actual number irrelevant here. Okay? Okay. So as a result of this, we say, all right, let's go ahead and plug in negative 4 into f prime. We'll plug in negative 1 into f prime, positive 1 into f prime, and 3 into f prime. Okay? So to start us off, let's go ahead and look at negative 4. So if we do that, we say, all right, if we plug in negative 4 into, say, this representation of f prime, just to make things a bit easier on us, what we can do is say, all right, this is 20 times negative 4 quantity squared times negative 4 plus 3 times negative 4 minus 2. So what this says is that we have, all right, we have 20 times something negative squared times negative 4 plus 3, so something negative, times negative 4 minus 2, so again something negative. So if that's the case, we have ultimately four factors corresponding to negative values. So ultimately, that means that we have, if four negative factors, the negatives all cancel out, so we end up with something positive here. All right. So now let's do a similar thing with negative 1 here, just to give you guys another idea of what's going on. So we have 20 times negative 1 squared, and then negative 1 plus 3 times negative 1 minus 2. So here, what we're going to have is 20 times, again, something negative, squared. But now we have negative 1 plus 3, so that's going to be something positive, and then times something negative. So here we only have 3 factors of corresponding to negative values. So this square part will make this positive, but we still have one extra negative factor here. So because of that, this is going to be less than 0. Okay? So if we were to employ the same logic on f prime of 1 and f prime of 3, then what would we get for a sign? Would we get something positive or negative for each of these two values? So let's start with f prime of 1. Would we get, using this logic here, would we get something positive or negative out of this? Negative, right. And how do we get negative?
Positive times positive times a negative.
Exactly. So we have 20 times 1 squared times 1 plus 3 times 1 minus 2. So this is positive times negative, so less than 0. And then f prime of 3 in a similar fashion is going to be what? Positive or negative? Positive. So 20 times 3 squared plus 3 plus 3 plus 3 minus 2. All these are positive, so we get positive out of this. Okay? So that's all good and all. So what this tells us is that means that all the values in negative infinity to negative 3 are going to have a positive derivative. All the values in negative 3 to 0 are going to have negative derivative, and so are 0 to 2. And then 2 to infinity are going to have positive derivative here. So let's go ahead and label that into our number line here. So we have f prime again. So negative 3, 0, and 2. So here we have positive derivative. So we're going to go ahead and label this with a northeast pointing arrow to indicate that. And then do the same thing with negative 3 to 0. So this is going to be negative. So we're going to have a southeast pointing arrow. And then 0 to 2 is also going to have negative derivative, so southeast pointing arrow. And then 2 to infinity is going to have a northeast pointing arrow because of a positive derivative. Okay? So what this ultimately tells us is that, all right, well, our increasing intervals, those are going to be from, well, negative infinity to negative 3, or 2 to infinity. So it's going to be from one of those. It's going to be from one of those intervals. So we have negative infinity to negative 3 union with 2 to infinity. Okay? And just to note that this union here indicates sort of or. That's another way of sort of thinking about this. Okay? But in a similar fashion, you might think, all right, well, decreasing would mean that it's just going to be negative 3 to 0 and 0 to 2, right? Well, yes, but here's what's gonna happen in the homework. So if you have something like this, where essentially it's just one interval minus 1 point, then in this case, log kappa will want you to sort of mesh the two intervals together. So in this case, so log kappa wants negative 3 comma 2 in a case like this. This. With only 1 point missing. Okay? So ultimately your decreasing interval in terms of plugging this into log kappa is going to be negative 3 to 2. Okay? Alright? So that's that part. So now step 3 from this is to say, alright, we've got our increasing and decreasing intervals. Now let's use the first derivative test to figure out how we can classify the relative extreme. Okay? So step 3. So classify critical points. Okay? So by the first derivative test, we have a relative maximum at x equals what? So in this case, if we harken back to our first derivative test, we have, if the first derivative goes from positive to negative, then that means we're going to have a relative maximum at that point. So in that case, that says, all right, well, the only time in which we have that is, well, -3, because positive to negative. So we have a relative maximum at x equals -3. But in the case where we have an actual function given to us, in this case, log kappa is going to want you to put in the actual xy points. So relative maximum at 3, f of -3. So in this case, if you want the corresponding y coordinate, you're going to want to plug in x equals -3 back into the original function. Original f of x. Okay. So if you plug in -3 back into this function here, then a quick little plugging into a calculator should tell you that this is going to be -3, 513. Okay. So that's the relative maximum part. And then similarly, we're going to have a relative minimum at x equals what points based off the first derivative test? Oh yeah, sorry. So, someone else?
X equals 2.
Yeah, x equals 2. Okay. So, relative minimum at, in this case, 2, f of 2, which is going to equal, well, in this case, if you plug in 2 back into the original function back up here, then it's going to end up being 2, -112. Okay. So like I said, ln kappa wants xy points when possible. Okay. So that's all 1A. So any questions on any of that? Okay. So let's move on to 1B. So yeah, I immediately kind of put part B on like the halfway point of the page because I thought we'd need more space for 1A, but apparently not. So yeah. Okay, so now the thing is that we still have to do the same thing in part B, except now we're only given the derivative of our function. So basically now let's just go ahead and just keep doing what we've been doing in the last example. So in this case, step 1, again, we have to first find our critical points of our function. But the good news is that the problem already gives us our derivative. So in this case, we just need to apply algebra, set it equal to 0, and see what happens, since our function here is defined everywhere in this case. So g prime of x equals e to the 2x times 3x squared minus 27. So in this case, if we want to solve for 0 in this case, what values of x would give us this equality here?
Negative and positive 3.
Right. Because in this case, what you'll notice is that if we factor out a 3 in this here, you'll get 3e to the 2x times x squared minus 9. But thankfully, x squared minus 9 has a nice factorization to it, right? It's just 3e to the 2x times x plus 3 and x minus 3 equals 0. So since exponential is never 0, the only thing that tells us is that we have x equals plus or minus 3 are your only 2 points here, are your only 2 critical points. So step one's pretty nice and simple in this case. So now let's move on to step two. So here, let's go ahead and draw our number line as we did in the last example. So G prime. So in this case, we're going to have -3 and +3. We're going to label our 0 points here, where we have G prime is 0. So in this case, if we pick our three intervals, -∞ to -3, -3 to +3, and then through to infinity, let's go ahead and pick some points inside each of these intervals to see what we get. So for this interval, from -∞ to -3, what value of x would you want to plug into G prime here? -4, okay. So plug in -4 into G prime. So if we do that, we say, all right, well, if we plug in -4 into here, we have, essentially we have 3 times each of the, well, in this case, -8 times, well, x, -4 plus 3 and -4 minus 3. So -4 plus 3, -4 minus 3. So in this case, we have what sign is for our derivative? Positive or negative? Yeah, we're gonna get negative though, because we have negative here and negative here.
Is the first term positive?
Yeah, first term is positive because remember, an exponential is always positive, right? So we're gonna get positive here. So that's the first one. Now let's go ahead and do the same thing for -3 to +3. So -3 to 3. So what would you want to plug into G prime here? 0. Okay, nice round number. So in this case, we get 3 times e to the 0 times 0 plus 3, 0 minus 3. So that should get you what? Positive or negative?
Negative.
Negative, good. So we get negative. And then for 3 to infinity. So as you might have guessed, a nice number to pick here would be just pick 4. So if we do that, we get 3e to the 8th power times, well, we get 4 plus 3, 4 minus 3, and so that should pretty quickly tell you that's all going to be positive. Good. So we did that. So this is going to be our number line here. So that should pretty quickly tell you that, well, in this case, our increasing intervals are going to be from -∞ to -3, union 3 to infinity. And then decreasing intervals are going to be from, well, in this case, just 1, from negative to +3. Okay? But here's the thing with step 3 in this case. So step 3, so by the first derivative test, we have a relative maximum, relative minimum at x equals what? So by the first derivative test, we have a relative maximum at x equals -3, and relative minimum at +3. Good. But here's the thing though. You might think, okay, well, what about the corresponding y values? Well, we don't have g of x explicitly given to us, so we can't do that here. So in this case, this is the best we can do. So best we can do, g of x isn't given. So unfortunately, this is the best you can do in terms of the classifying relative extreme part of your problem. So that's part B. So
I'm just wondering why x equals 0 isn't a critical value.
because the fact that if you plug in x equals 0 to the derivative, you get something negative. So in this case, you don't have if you don't have x equals 0 as a critical point, because in this case that your derivative is strictly negative. So in this case, it's not 0. So, okay. Any other questions on anything? Yeah. So the only reason it was a critical point in part A was because of the fact that that was just sort of how the problem played out. So, okay. All right. Any other questions on part B? All right. So let's move on to example 2 then. So the thing is that the critical numbers of f of x equals 2 times cosine of 2x plus 2x on 0 to 2 pi are pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. Find the x values at which f of x has a relative maximum and a relative minimum. So if you remember this problem, if you take a look at this function here, you may notice this looks a little familiar. And it will, because this was exactly the function that we saw last time. So the thing is that in this case, instead of going from 0 to pi, we now go from 0 to 2 pi. So in the context of the last lesson, if we just went from 0 to pi, these would be the only critical points we care about. But now since we're going from 0 to 2 pi, now we have 2 more critical points to take care of, which would be the ones we discounted last time. So just a quick little remark on that. So aside from that, let's go ahead and do the usual 3-step process here. So in this case, the problem only asks us to find the x values at which we have a relative max and min. So again, we don't care about the corresponding y coordinates in this particular case. So with step 1, again, f prime of x, well, quick little derivative computation yields that f prime is what? Now let's give someone else a chance.
Negative 4 sine of 2x plus 2.
Yep, negative 4 sine of 2x plus 2. So you can either say, okay, well, we did this last time, so that's what we got. Or you can say, all right, well, if I don't remember that, then a quick application of chain rule will give us an extra factor of 2 over here. And then the second term is just power rule, so nothing much to that. So in step 1, well, the critical points are already given to us, so CP's already given. So on to step 2. Okay? So step 2. So let's go ahead and draw our number line. So f prime. So I'm going to say, all right, we're going to go from 0 to 2 pi in this case, because that's our domain in this particular context. So now we're going from, we have our critical points are pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. And this is not necessarily to scale, but let's pretend for the sake of the problem it is. All right. So in this case we have sort of 5 intervals we have to consider here. So in this case we have 5 values of x we got to plug into f prime. So for the interval 0 to pi over 12, what would be a good value to pick for that, do you think? What's that?
You pick a 1.
So you have to pick something from between 0 and pi over 12 in this case. So in this case, one good value you could pick is say, all right, well, you could just pick the point that's directly in between the middle of these. So in this case, the point that's directly in between 0 and pi over 12, well, you could pick pi over 24. Okay? And then for the second interval, from pi over 12 to 5 pi over 12, what would be a good value to pick there? What's a value that's in between those two that could work?
Pi over 6.
Yeah, pi over 6. Or if you want, you could say, all right, this is 2 pi over 12, just to say, okay, now the reason this is in between pi over 12 and 5 pi over 12 is because of this. Right? And then the next interval, 5 pi over 12 to 3 pi over 12, would be what? What could be a good point to pick in there?
Just pi.
Yeah. In this case, yeah, that could work. Yeah. So pi, because that's just pi over 12 divided by 12. So then next interval, 13 pi to 17 pi over 12. What could be a good value to pick there? What would you want to pick in between here?
Pi over 12.
14 pi over 12, that could work. And then f prime, and the last interval, 17 to 2 pi, or 17 pi over 12 to 2 pi. So one thing to note is that this is just, well, 24 pi over 12. So in this case, you could just pick any value between these two. So in this case, you could just pick, say, 20 pi over 12. Okay? So in this case, what you want to do to say, all right, is this going to be positive or negative? Your best bet would be to just use a calculator. So plug into a calculator. So and make sure, and of course, make sure to keep this in radians. Okay. So tell you what, why don't we sort of do this? So I'm going to have, let's see. I'm going to have you two plug in pi over 24 into f prime. I'm going to have you two plug in 2 pi over 12 into f prime, you two. And then, let's see, you two plug in pi to f prime, and then I guess you two can plug this into 14 pi over 12. And then I'll just say, okay, if you plug in 20 pi over 12, you should get something positive. So yeah. Okay. So, why don't you guys take a second to do all those computations, and then we can work on it from there. And again, we only care about if it's positive or negative. So. So, sounds like you got something. So.
Yeah, negative.
Yeah. So 2 pi over 12 is negative.
Yes.
Okay. Good.
For pi, I got positive.
Okay, you got positive. Good. Okay. And then 14 pi over 12. I guess. Okay, we got positive for pi over 24. Good.
We got positive.
I'm not getting positive for that. So in this case, you should end up with something negative here. Okay. So in this case, we have positive, we got negative, positive, and negative. So in this case, you'll get something alternating here. So step 3. So in this case, we only care about the x values at which we have a relative max or min. So in this case, relative max and relative minimum. So we have relative maximum at x equals which 2 points?
X equals pi over 12 and x equals 13 pi over 12.
Yep. X equals pi over 12 and 13 pi over 12. And then similarly, we have a relative minimum at 5 pi over 12 and 17 pi over 12. Okay. And, well, that's example 2 because the x values here are the only thing we care about here. So that's that. Okay. So any questions on any of that? Okay. So that's all the exam 2 material for exam 2. So, like I said, exam 2 review is on Friday, so come with any questions. I also have office hours on Friday if you guys have any last minute questions as well. But otherwise, I will see you guys either Friday, or either this Friday or sometime next week. So if I don't see you before the exam, good luck. So, yeah, see you guys then.